Hello, welcome to Astronautics for Exploit. This is Dr. Ayanshola Ogunele. Dynamic management and seamless integration of multi-orbit satellite constellations. Imagine an approach for combining low Earth orbit, medium Earth orbit, and geostationary Earth orbit strengths. Dynamic management and seamless integration of multi-orbit satellite constellations. An emerging approach to connectivity uses advanced software and technology to provide resilient, flexibility, and high-performance communication services by intelligently selecting the best available orbit and satellite service for specific application needs. Multi-orbit connectivity combines the strengths of different orbital regimes: low Earth orbit for low latency and high speed, geostationary Earth orbit for wide coverage, and medium Earth orbit for a balance of both. Dynamic management involves real-time traffic optimization, dynamic bandwidth allocation, and orbit switching based on application needs, network performance, and location to ensure efficient resource utilization. Seamless integration ensures an uninterrupted user experience, much like a cellular network, where the system automatically switches between available satellites and orbits without manual intervention. Dynamic management and seamless integration of multi-orbit satellite constellations are achieved through advanced technologies and solutions such as hybrid network management, intelligent orchestration, dynamic routing, automatic secure switching, software-defined platforms, enhanced redundancy and resilience, and a host of others. The focus points are as follows: satellite constellation and dynamic management and seamless integration of multi-orbit satellite constellation. Satellite constellation. Multi-orbit satellite constellations combine satellites operating in different orbital regimes such as geostationary Earth orbit, medium Earth orbit, and low Earth orbit into one seamless integrated network. The goal of multi-orbit constellation is to leverage the unique strengths of each orbit in order to provide a more robust, flexible, and high-performance connectivity solution than any single orbit system could offer. Tesla Telesat Lightspeed constellation is shown in this picture. A multi-orbit system dynamically routes user traffic to the most appropriate satellite network based on real-time needs such as latency, required bandwidth, and location. For the routing, the dynamic routing is facilitated by advanced ground infrastructure and user terminals such as electronically steered array antennas for in-flight connectivity. Illustration of satellite coverage for telecommunication services is shown in this picture. Dynamic management and seamless integration of multi-orbit satellite constellations are as follows: dynamic traffic steering, management and routing, advanced ground and user terminals, seamless handover mechanisms, dynamic resource allocation, inter-satellite links, integrated network management and orchestration, network orchestration and redundancy, and cloud computing and mobile edge computing. Dynamic traffic steering, management and routing. The system employs a sophisticated network management layer which acts as intelligent switchboard. When a user requests a service, the system assesses the requirements: latency-sensitive traffic, high bandwidth, less latency-sensitive traffic, and mission-critical service. SES multi-orbit strategy is shown in this picture. Latency-sensitive traffic such as video conferencing, online gaming, cloud access is automatically directed to the LEO network due to its close proximity to the Earth and low. High bandwidth, less latency sensitive traffic such as streaming video, bulk data transfer might be routed via the high capacity geostationary Earth orbit or medium Earth orbit satellites. Mission critical traffic can utilize redundancy of multiple orbits for resilience. Orbital design optimization for large-scale cell constellation is shown in this picture. User terminal, advanced ground and user terminal is another dynamic management and seamless integration of multi-orbit satellite constellation. User equipment, such as on aircraft, ship, or remote ground station, is designed to be multi-orbit compatible and network agnostic. These terminals, often using electronically steered antennas, can automatically track and switch between satellites in different orbits and frequencies. This enables users to be able to maintain a continuous connection even as LEO satellites move rapidly across the sky. In-orbit target-based autonomy for enhanced stability of small satellite constellation is illustrated in this picture. The ground infrastructure must be able to manage endeavors and coordinate communications between satellites in different orbits. Eutelsat multi-orbit geo-LEO satellite network is shown in this picture. Seamless handover mechanisms in order to ensure continuous service as satellites move or traffic is rerouted, network performs seamless handovers. As a LEO satellite moves out of a terminal's view, the system prepares the next available LEO satellite to take over the connection without any interruption. The system can also hand over a session from a LEO network to a MEO or GEO network, and vice versa. Illustration of the use of artificial intelligence in transforming geospatial intelligence is shown in this picture. Multi-orbit networks. Because LEO and MEO satellites are constantly moving, the system must manage frequent handover events, transferring the connection from a disappearing satellite to an incoming one. Multi-orbit networks make use of sophisticated handover management framework which can predict satellite trajectories and enhance quality. Satellite constellations for the mitigation of environmental and other effects is shown in this picture. Dynamic resource allocation. Systems must dynamically allocate resources such as spectrum, power, bandwidth in order to meet fluctuating user demand and changing environmental conditions. Telesat Lightspeed constellation is shown in this picture. Intersatellite links. Satellites within and between different orbits can communicate directly with each other using intersatellite links, which is usually laser-based. It enables data to travel in a space-based mesh network, potentially bypassing ground stations entirely over long distances. Illustration of satellite mega constellation is shown in this picture. Technologies like laser-based optical links allow satellites to share data directly with each other in space. This thereby reduces reliance on extensive ground station infrastructure and enable faster data transfer across the network. Vast space relay communication concept for multi-orbit mission is shown in this picture. Integrated network management and orchestration. The overall network architecture treats the different orbits as a single fragile pool of resources, and this orchestration allows for load balancing, automatic rerouting, and overworking control system manages the entire constellation. Illustration of the proliferated constellation is shown in this picture. Cloud computing and mobile edge computing. Incorporating mobile edge computing and in-network caching technologies helps process data closer to the user, thereby reducing latency and network load. Illustration of low Earth orbit satellite constellation is shown in this picture. For more information, contact Astronautics for Exploit. You've been listening to Dynamic Management and Seamless Integration of Multi-Orbit Satellite Constellation, Emerging Approach for Combining LEO, MEO, and GEO Strengths by Dr. Enshola Ogundele, with the focus point, satellite constellation, and dynamic management and seamless integration of multi-orbit satellite constellation. Thank you